So today we have a guest speaker. Her name is Xiaoqing Ge, and Xiaoqing is currently a senior innovation engineer in the Advanced Analytics Center of Excellence at Baker Hughes Energy Innovation Center, which is based in Oklahoma City. Here she adapts and applies disruptive digital technologies to drive customer valued outcomes. Xiaoqing is a multidisciplinary engineer with expertise and experience in machine learning, deep learning, computer vision, edge devices, system modeling, simulation, and advanced control system designs and optimization. At Baker Hughes, Xiaoqing has worked on a breadth of problems, including deep learning, enabled smart inspection solutions, edge acceleration image analytics platform, reliability analysis and predictive data analytics, reservoir modeling, optimized oil field power solution, and more. Before joining Baker Hughes, Xiaoqing was a senior technical professor at Halliburton Automation Center of Excellence, or professional, where she designs and implemented next generation automation and advanced control systems for drilling operations. She invented or co-invented 11 U.S. patents in the areas of data fusion, sensing, advanced control system, and fault detection. Xiaoqing received her BS degree in automation and control from University of Science and Technology in China, and her MSc and PhD degrees in electrical engineering from Rensselaer Polytechnic Institute. Today she'll be giving her presentation titled A Shallow Intro to Deep Learning and Computer Vision. So with that, Xiaoqing, I'll turn it over to you.
Thank you for the introduction, and thank you everyone for your time and interest today. So I think I really appreciate the opportunity for me to share the knowledges and learnings on AI, deep learning, and computer vision today. And hopefully this talk could plant seeds for some new ideas and future collaborations between us. So today I'm going to give a talk on a shallow intro on the deep learning. And really the presentation is tailored to expand the breadth to cover the spectrum of computer vision using deep learning technologies instead of going like deeper on the technical side. So it's based on my understanding and experience working on CV projects. And I think I will call it a success if we walk out of this presentation with like a better understanding of the difference between deep learning, AI, machine learning, and why deep learning has become so popular and powerful recently. And maybe think of cases where you can apply the computer vision technologies to your problems, either professional or personal. And probably before I start the presentation, I do want to spend a few minutes just introducing our center. We are new to the digital solutions big family, and we want to know the big family better and vice versa. So Energy Innovation Centers used to be called Oil and Gas Technology Center. It used to be one of the 9 global research centers back in the GE time, but it's dedicated to the oil and gas industry. And then we became part of GE Oil and Gas and eventually Baker Hughes. And now we report directly into Scott Parent, who is the VP of Engineering Technology, and there are currently 3 teams in our center. The first one being the one I'm in, called Advanced Analytics Center of Excellence, focusing on AI, deep learning, computer vision, and data analytics. We have quite a few projects with Waygate on AI-enabled inspections, and we're currently expanding the collaboration to other businesses such as Valley, Nevada, and Access Controls. And the second team is Energy Operations team, who focuses on edge devices, analytics, and platforms for various applications. And the third one being Energy Transformation team, whose vision is to establish our leadership in decarbonized energy through reducing the carbon footprint and really the energy diversification. Okay, with that, I'll go into the presentation and of course start with a safety moment. So I think really in 2020, one theme is really the new normal. And because of COVID-19, it really changes the way we used to live. And every industry and individual are fighting the pandemic in their own way. And here I'm just want to list a few applications where computer vision technologies actually stand at the forefront in the fight against the virus. And the first case I want to highlight is to use intelligent video analytics really to monitor the urban spaces. And with the technologies, we were able to measure what, when, and where, and as well as how things are moving in streets and open spaces. We can also answer our questions such as are people maintaining safe social distances, what surfaces are people touching that may need cleaning, and how many people are wearing masks, and so on and so forth. Another applications, if you look at the right top side, so it is really an application that is developed by several students where they use computer vision techniques to calculate the distance between people through bounding box coordinates as well as the depth of the person. So with that, they were able to flag any trace of violation of social distancing using the techniques based on video frames. And so the third one is not like a real novel applications because researchers have been using deep learning or computer vision technology for diagnostics. And this is applications dedicated to COVID-19 diagnosis, where we can use deep learning techniques on radiological imaging for quicker diagnosis of COVID-19, and it also can be used to validate initial screen results or immediately screen patients. Last but not least, the fever detecting cameras. They are equipped with facial detection techniques, and which can help speed up the security checkpoints while identifying individuals that may have symptoms, be the early stage of the virus. It also has been already deployed in several countries, really to provide a fast and contactless way to help prevent spread of the virus. And the point I really want to make is that we don't have to be PhD expert in computer vision to make an impact. Really, the democratization of the technology actually has made the technology so accessible. So people like you and me, they are actually leverage the technology for different applications. There are so many open source computer vision models out there that are already trained on a super large data sets, so we can directly leverage them. They are also very affordable but powerful edge devices, such as Raspberry Pi or NVIDIA Nano, just some TX2, name it, for you to deploy a model on. And thanks to those who had made the deep learning framework so easy to work with, we can actually build our own model starting from scratch. So if you have any ideas, just don't hesitate and just starting working on that. So really, this is the outline of the presentation. I'll start with an overview of the computer vision technologies and then segue into how actually deep learning works and revolutionize the computer vision area. Then I'll compare the deep learning method with the traditional method and followed by a survey of Baker Hughes applications. And I'll conclude the presentations with some looking ahead of the future directions. And if you have any questions, do not hesitate to ask them. And we can also probably leave the question to the end if we have 5 or 10 minutes left. Okay, so what is computer vision? So it is really a field of study that seeks to develop technologies to help computer really see and the content of digital images. There are really two elements of it. It's the digital content and the algorithms to understand and interpret it. So when you look at the video here, right, so you naturally see buildings, cars, people, and other objects. The cars keep moving as the traffic light is green and pedestrians are either walking or waiting on the sidewalk and no one is walking across the street. And if you look closer, you can infer much more information from the picture based on your past experience or similar scenes you have encountered. But to a computer, this is never easy. It actually took researchers and engineers decades to reach this point. And to have a computer vision model that automatically identifies the class, the location of an object, and probably tracks its movement in real time. We'll talk about why it's challenging in a few slides, but needless to say, this is actually an amazing milestone in the history of computer vision, which lays the foundation for autonomous driving and many more other applications. So like many other fields, right, computer vision is an interdisciplinary field which involves the processing of acquiring, processing, and analyzing digital images. So it actually borrows technologies from, or either borrow technologies from, or benefiting a wide range of science and engineering fields, including AI. Let's start with AI, artificial intelligence. So computer vision is actually a subfield of AI, with which it shares a lot of topics such as pattern recognition and learning techniques. For robotics, it's probably like a well-established field where we have used computer vision to help robotics see things, really improve the robotic version, and help them achieve vision-based tasks such as autonomous navigation. Signal processing is really something we can borrow techniques from. It's a very well-established field too, and many methods of 1D variables used, such as temporal signals, can be extended to process multivariable signals in computer vision. And needless to say, physics explain the behavior optics, which are a core part of most imaging systems, and various measurement problems in physics can be addressed using computer vision. For imaging, it's also a very closely related field because computer vision relies on image sensors, either visible or infrared light. Neurobiology, I do want to highlight this one because specifically the study of the biological vision system plays a very important role in computer vision. And over the last century, there has been an extensive study of eyes, neurons, and brain structures that are devoted to the processing of visual stimuli in both humans and various animals. And this has led to a coarse but very complicated description of how real vision system operates in order to solve certain vision-related tasks. Last but not least, mathematics. Beside the above-mentioned views, almost all computer vision problems can be studied from a purely mathematical point of view, and many methods in computer vision are really based on statistics, optimization, or geometry. So really, the advancement of CV is a success for multidisciplinary collaboration, from a streamlined design combining software and hardware, and its success is going to benefit various areas and industries. Okay, so why is computer vision challenging, right? So analyzing a visual image appears so simple to us because it's kind of like our natural ability to see something, even for very young kids. But initially, CV was also believed to be a trivially simple problem that could just be solved by a student connecting a camera to a computer. However, after decades of research, computer vision still remains an unsolved, at least in terms of meeting the capabilities of human vision. It is still one of the hottest research areas today. And really, to answer this question, we first need to understand how computers are engineered to process the imagery data. So if you look at these pictures within seconds, you can tell this is an image of perhaps Lincoln or at least a male human being. But to a computer, this image, like all the other images, is an array of pixels, which are numerical values that represent the grayscale of brightness, typically on a scale from 0 to 255, with 0 being black and 255 being white. And what makes things even more complicated is that computers don't know colors, they just know numbers. So we have to use some kind of color model to convert colors into numbers such that the computer can process it. And the most common one being the RGB model, as many of you know that. For digital images, we have 3 channels, red, green, and blue. And so a typical color image is represented in a 3D matrix. So because of the way the computers are designed, so they are not good at solving problems and sometimes intellectually difficult for human beings. So they are very good at solving problems that can be explicitly described or formulated by a list of mathematical formula or rules. Usually problems is associated with structured data, and here by structured data we mean data or that is very well formatted and organized. In contrast, it is kind of hard or challenging for computers to make sense of photos and videos like humans do. We human beings naturally perform very well on problems with unstructured data, such as images, text, videos, and audios. Interpreting them are very easy for humans to perform, but hard to describe formally. Usually we do it out of our intuition. And that is exactly the reason why researchers are spending so much effort on artificial intelligence, really to understand and mimic the way how human brain works to solve the problems that are intuitive ours, but hard to describe it formally. And that's still not the end of story. If you look at the right of the slide, so there's some also other challenges make it difficult for a computer to understand images. And I've included a few scenarios here, but definitely not limited to these four cases. So in real-world applications, the same object can have different positions and angles in an image depending on the relative position of the object and the observer. And different images can have different light conditions. And in this part, though it is very dark, we can still recognize that as a rubber duck. But for computer vision, that may not necessarily be the case. And images may not also necessarily be complete. Some small or large portions of the images might be hidden, which makes the detection even more difficult. And to make things more complicated, some images might blend into the background of the image. So even for this image, it takes us several seconds to identify there's a human actually standing in a pile of logs. So really, to sum up, like there are several reasons for why it's challenging for computer vision tasks, and really being the lack of an effective approach for computers to process and understand the unstructured imagery data. Second, being our limited understanding of our biological vision system, and as well as the complexity of vision perception in a dynamic and nearly infinitely varying physical world. Okay, so I think appreciation of these challenges really also help us understand the history of computer vision better. Most humans, or most of us assume that modern minds create the concept of artificial intelligence, but actually our ancient ancestors already put forth some series of thinking robots. And ancient Greek mythology actually has predicted the rise of several modern technologies, including artificial intelligent robots and self-driving vehicles. An example of this is called like Taylor's, who is a machine made up of bronze and looks like a human being. And his task is really to defend the island of Crete. However, these historical narratives don't accurately describe the kinds of artificial being developed by today. And much of what we know today about visual perception comes from the neurophysiological research conducted on cats in the 1950s and 60s. By studying how neurons react to various stimuli, two scientists actually observed that human vision is hierarchical. The neurons detect simple features like edges and then feed them into more complex features like shapes, and then eventually feed them into more complex visual representations. And the study of the brilliance of our human body really marks the beginning of the journey of modern computer vision. But this journey is never smooth. Since then, it has turned out to be one of the most difficult and frustrating challenges in AI over the next 4 decades, which did not gain great success until 10 years ago. But the early computer vision task actually began earnest in the 1960s at universities that really viewed the projects as a stepping stone to artificial intelligence. Some early researchers were extremely optimistic about the future of this related field and actually promote AI as a technology that could transform the world. And really, the hype earned the researchers millions of dollars from public and private funding. And in 1966, two researchers of artificial intelligence at MIT actually launched a 2-month summer vision project really to create a computer vision system that could identify objects in images. And really, the task is to determine which pixels belong to which object, what is called the pixel-wise classifications in our current world. And at the time of this project, the domain branch of artificial intelligence was still symbolic AI, which is also known as rule-based AI. So what it means is the programmers actually manually specify the rules for detecting objects in images. But the problem was that objects in images could appear from different angles and different lighting. There might be obstructions or blending into backgrounds. Each of these scenarios generates different pixel values, and it's almost impossible to create a manual rule sets for every scenario of them. So naturally, the summer project didn't go very far and yielded very limited results. So with the tremendous optimism, researchers actually raised the public expectations so high, but failing to appreciate the difficulty or the challenges of the task. So by 1970s, governments and corporations actually were starting losing faith in AI. And with funding dried up, the period that followed became known as the AI winter. And since then, AI has been progressing very slowly or even stagnant. The main effort on computer vision has been focusing on extracting handcrafted features from images to understand it. And it works under certain conditions, but subject to a lot of limitations. So in the 1980s, a French computer scientist, Yann LeCun, actually introduced an idea called convolutional neural network, which laid the foundation for the deep learning-based computer vision we're using a lot today. And fast forward to the 21st century, really as the internet became a mainstay, computer scientists gained so much access to more data than ever before, and computer hardware continued to improve as costs went down. The rudimentary neural networks and algorithms developed very fast in the 1980s and 90s. So more than half a century old, the field of artificial intelligence actually finally had its breakthrough moment in 2012 at the ImageNet Large-Scale Visual Recognition Challenge. And actually, a team from the University of Toronto entered a deep learning network called AlexNet. That really changed the game for AI and computer vision. It actually achieved an error rate of 16.4. It may still seem high for us, but in years following, it has gone down quite a bit. And we have to know before that, the best error they can achieve is 26%. So since then, the field of computer vision really has witnessed continual advancements in really the past 5 to 10 years. And now deep neural networks are the golden standard for image recognition tasks. And this achievement really paved the way for the advancement of other AI applications. So what are the popular computer vision tasks? So I really divide them into 3 major categories, with the first one being image recognition, which is still the majority of computer vision tasks we are solving today. And there are a few subcategorized under image recognition, being classification, which means for this image, we just need to classify as an image with belongs. And going one step further, called object detection. In addition to the class of the images, we also want to localize the objects of each belong. And we can also have deep learning models to either semantically segment images, really have the pixel values highlighted for those belongs, or even have segmentation for each instances. Instead of segment all the belongs, we can separate out each individual mask of each belongs. And the last category really being the landmark detection. So 2 applications include face landscape recognition, or face landmark recognition, which really extract some important features from your face, help researchers to quickly and efficiently and accurately detect the face from different persons rather than analyze the whole pixels of the image. Another one being really uses to detect the gesture or track the gesture of a human being or other objects. The second emerging category really being image generation. So more and more applications have been focusing on how do we generate more images for different purposes, such as if we are lacking training images data for deep learning, we can generate some really real images to train the model. And so some applications include really generate image or restore the image, denoise the image, or upscaling the image resolution. And the one interesting application I really like is neural style transfer. It's combining the content and the style of 2 images. It generates a new piece of art. So really the technologies behind the image generations, the most popular one being called GANs, which the full name is Generative Adversarial Networks. I won't go too details into the technologies, but really want to probably talk about the ideas, how they generate the image. I think it's really brilliant. So it really consists of 2 neural networks, one with one competing against each other. That's why it's called adversarial. In order to generate some new synthetic instance of data that can pass for real data tests. These are widely used in image generation, video generation, and voice generation. And the basic idea is really to having one neural network called generator to generate fake images while the other one, the discriminator, takes both real and fake images and determines the probability of it being real. These two networks are dynamic and both keep improving themselves in two feedback loops. So the competition makes the fake images more and more real. An analogy would be like the opposition of a counterfeiter and a cop. Really, both sides are learning, and while the counterfeiter is learning to pass false notes, the cop is really learned to detect them. So both of them learn each other's methods in a constant escalation. So the last one being really the video analytics. So if we divide a video into different frames, there's no difference between the image recognition tasks, but we may have some additional tasks such as we may want to track or relay different frames within the image to detect if there's the trajectory of an object or detect if there's an event happening. Any questions before I move on? Okay. So why do we need to use deep learning? This has been a question a lot of people have discussed. So really, first let's see like what's the difference between AI, machine learning, and even deep learning. So deep learning is really about like learning across many layers of neural network accurately, efficiently, and without supervision. And so first start with AI, artificial intelligence. It starts from 1950s, where John McCarthy, who is widely recognized as one of the godfather of AI, defined the AI as the science of engineering of making intelligent machines. So a computer system to able to perform tasks that normally require human intelligence to do, and includes machine learning and good-fashioned AI, such as rule engines, expert system, or knowledge graphs. And machine learning is really a subset of AI techniques. And one aspect that separates machine learning from the rest of AI technologies is really its ability to learn from examples without being explicitly programmed. The learning part is essentially an optimization algorithm, usually attempting to minimize error or maximizing the likelihood of their predictions being true. And artificial neural networks is a computational models inspired by animal central nervous system. If you look at the animations here, so it is actually an oriented graph, which consists of nodes, which in the biological analogy represent neurons. And they are connected by arcs, and like dendrites receive inputs to the synapse of the other neurons. It receives multiple inputs from multiple arcs, and each one associated with a weight of each node. The soma processes this incoming signals over time and converts that processed value into an output, which is then sent out to other neurons through the axons and the synapses. And in a similar fashion, the perceptron actually applies the values received as input, and activation function decides what signal to pass to the next perceptron. In short, like the human brain, artificial neural network is composed of many computing cells or neurons that each perform a simple operation and interact with the other to make a decision. And really, deep learning are algorithms which use deep artificial neural networks to build a hierarchy of data representations. And here, deep is a technical term. It really refers to the number of layers in a neural network. And people really call it deep. It's actually over 3 layers. And in actual, a lot of deep learning used today actually use hundreds of numbers of layers in the network. So deep learning really mimics the brain structure to solve computer vision problems and some other artificial intelligence problems. It is thought that visual processing in the brain is actually hierarchical. So we know one layer feeds into the next and computing progressively more complex features. Some early visual cortex compute simple features such as edges and then sends the output of that computation to the next visual area. And each visual area computes a slightly more complicated feature than the area it received the input from. And by the time this computation reaches decision-making areas of the brain, they are sufficiently abstract so the object recognition or any other task can be done relatively simple. And this is really the inspiration of the layer design of CNN. And the development of CNN actually has a tremendous influence in the field of computer vision. So how exactly does deep learning work in computer vision networks? So this is really like an architecture or flow of how a typical deep learning-based computer vision task is done, starting from the left with the input images. So actually, almost all of the deep learning computer vision models are based on the CNN, which, as we just talked about, is a special type of ANN. And the early ANN models consist of fully connected layers, which means all the neurons between the layers, they are connected to each other. So this means there's a tremendous amount of parameters we have to identify, and definitely not in an efficient way, as a lot of weights actually are close or actually zero, indicating there are non-active connections between the cells. So CNN actually improves this by introducing the idea of convolutional layers. So instead of having a big fully connected layers, so they have smaller size convolutional layers, which the analogy will be some filters to detect the features with relatively small size and usually multiple of them to extract more than one features. And the most important feature is that the parameters of filters, we don't need to actually handcraft them. It can be learned automatically to extract specific features for different applications. That really enables the deep learning model to learn the features that matters most to predict the desired outcome by themselves. And some other important building blocks in CNN here. So we know in addition to convolutional layers, there are also pooling layers. So the purpose of using them is really to remove some redundancy present in the input feature while still keeping the critical information to speed up the training process. It also reduces the amount of memory consumed by the network and prevents model overfitting. Really, in the structure, there are multiple of them finally follow through some fully connected layers. They're really at the end of the model, and the purpose of them is to flatten and keep all features from the previous layers. And then depending on your computer vision task, you can either have something to predict the class, usually a softmax function, class the classification, or generate a bounding box of your object detection, or have additional convolutional layers to predict some segmentation maps. And here I do want to have some animations just showing how training and inferencing is done in deep learning computer vision tasks. So this is a task which we really want to identify the digits and digitize them into 0 to 9. So usually neural model training is essentially an optimization problem to minimize the prediction error. And they use the gradient descent to iteratively update the weights based on the prediction error. And in each iteration, it calculates the error from the input in this way, and then pass the error in back propagation to update the weights. The iterations continues until a satisfactory criterion has been met. And then once the model is pre-trained, it is used to detect or inference on other cases. Here, so it was used on new images, and then in the digital classification example, it applies the pre-trained weights to find the digit with the highest probability after all the calculation. The highest probability is 7, and it categorized into this category. So that is really a simple example demonstrating how it works in training and inferencing. So we know like deep learning really has revolutionized the deep computer vision and AI in general. And many problems that once seemed impossible to be solved are actually already solved to a point where machines are obtaining better results than humans. And here, probably image classification is a good example of this. So in the left figure, I'm including a plot actually showing how the deep learning models evolve, with the y-axis indicating the prediction error of each model. And starting from here is deep learning based model, starting with AlexNet. So we mentioned it is the first CNN model that actually improved image classification on a very large data set by almost 10% regarding the top 5 test error. And since then, there's a variety of, excuse me, of CNN methods have been developed and submitted to the competition. Second one, a famous one being the VGGNet, which actually includes a very simple 19-layer CNN. And then GoogleNet proposed a new complex module named Inception, actually allowing several operations like pooling and convolution layers to be working in parallel. And here I do want to highlight ResNet, which is also have another name of Microsoft Deep Residual Network. What it does is, excuse me, it took the lead on both internet classification and also COCO detection and segmentation tasks. It introduced the idea of residual connections, which enable an ultra deep learning model. As you can see, the number of layers actually jumped from 22 to 152 layers. And this model actually achieved a very incredible performance of 3.6 top 5 error, which means for the first time, a computer vision model actually beat the human brains or human performance, which is about on average 5 to 10% error in image classification. And in the last few years, so several variations of ResNet have been proposed, and ResNext actually outperformed its original version using half of the layers, and the problem of supervised image classification is actually regarded as solved. And the ImageNet classification challenge actually concluded in 2017. So this really shows how computer vision models improved over the last few years and really achieve or beat human performance in image classification tests. And the right view, it may show a little bit like overwhelming and busy, but what I want to show here is really how the models compares with each other for the most popular ones used currently in terms of their computational complexity as well as their performance. So there are really some clusters, and really the recommendations for most of researchers is first define your problem and really narrow down your options to a few and really test them on your own images. There's no like golden rule of thumb, like which model to use for each case, but sometimes it really takes try and error to find the best one that fits your application. So with the advancement of deep learning, many people may ask, like, has deep learning really superseded traditional computer vision algorithms? Or in a similar vein, is there still a need to study traditional computer vision techniques when deep learning seems to be so effective and attractive? I would say the answer is no, at least for now, because deep learning is still only a tool of computer vision, and actually it's certainly not the solution for our problems. And because before the emergence of deep learning algorithm, the traditional CV actually relies really heavily on handcrafted features here. So there are SMEs or domain experts involved to extract some features they think that are important to identify or classify the image. And as we mentioned earlier, the deep learning actually get rid of that task. It's doing feature extraction and classification in an automatic and optimized way. So it's really have very impressive performance, which means it's very fast and accurate in image recognition and other tasks. And it's very flexible and easily scaled up to other problems compared to the hand feature extraction. But that also means deep learning is very, very data hungry. So it needs a lot of data. So to give you an idea, those famous image classification models mentioned above are training on data sets on the order of millions of images. So for example, the ImageNet, it has been trained on 1.5 million images with 1,000 object categories or classes. And definitely the data collection or annotation effort is not trivial. And another, probably I would say the disadvantages of deep learning is that it's actually a black box. It does not provide a lot of visibility or you can interpret why the model is taking the parameter like this. But compared to this, the traditional method usually offers a full transparency. So with that, you can actually better gauge and judge whether your solution can work outside of a training environment. And you have better insights into a problem that you can transfer into your algorithm. And I would say using traditional computer vision actually help you understand a lot of ideas in deep learning. And by understanding the concept better, we can actually borrow some techniques from traditional methods like data augmentation or processing to improve the performance in deep learning. And to sum up, the answer really depends. I say don't only use the deep learning because it's trendy. And traditional methods still are very much useful and actually perform very well on a lot of well-established problems. And actually, they can save you a lot of time and many headaches in preparing such a large data set for deep learning. So here I want to spend probably 5 to 10 minutes talking about the computer vision applications within Baker Hughes. A lot of them are done at EIC, but also we have sister organization called Avatars, which also have a lot of experts in CV and data analytics. So the first category is really computer vision at the edge. And why we're doing it at the edge compared to doing it on the cloud is really the limitation of where the application is. For example, when we have applications, we need to install some computer vision devices or algorithm in remote sites, which has no connectivity at all. Or we may need to install them on a mobile device, and the signal is not always available when the truck is driving. And in that sense, we are doing computer vision analytics actually at the edge. And usually they are enabled by some edge devices, which one being NVIDIA Jetson and TX2, which are very small pieces of edge-based GPUs, very low power consumption, and the cost is probably $400 or $500. And what we use, where we use it is the first case being called SafeSite. It's actually an application. We do smart logging of site activity at some remote sites. It's skid mounted. It's solar panel powered. It's a self-contained system used to monitor the site and personnel safety, as well as to track the field activities and validation some field activity for transaction purposes, and as well as doing some security surveillance of the site. Another application is a kind of like sister application, which we call SafeSense, where we actually apply a lot of sensors with edge GPU devices on our Baker service trucks. So because in North America, we have more than 4,500 service trucks running in the field every day. So they have very unique access to the field activities and some remote sites. And by outfitting these trucks with relatively easy to install, low cost sensor kits with the GPU edge devices, we're able to collect some unique information that hasn't been collected before in a new manner with a very good temporal and spatial coverage. Some examples here as we use sensors on the truck to monitor emissions, to monitor road conditions along the way it has been traveled. And most importantly, how do we do better navigation on the mixed roads, which is not available through Google Maps? And another application was being, can we use the edge devices to run computer vision models to detect some objects? For example, drilling rigs, pump jacks on the activities while we have the location. We are collecting some unique information that oilfield data providers are very interested in. So the second category I would call AI-enabled inspections. So one being called Integrate, which is a collaboration effort between our team and OFS drill bits organization. So we know currently the drill bits, they are graded in a manual way, meaning there are some operators actually take a look at the bits and give a score to each bit based on his experience. And of course, that is manual operations, and it's really very subjective. And really, what we want to do is let's have a computer vision process to standardize it, to speed it up, and to make it more accurate and reliable. And the first application we have been working on is really using classification models to give each of the bit on the tooth of the bit classification based on the IEDC standard. And then a second phase will be apply a more advanced model, for example, segmentation of to quantify the cutter wear. And another sub application is here is really how do we use some text recognition techniques to digitize, to speed up the reading of the bit records. And we were told that there has been like several hundred man-hours spent per week just to enter the paper format digits into their system. And definitely by introducing this, it can greatly reduce the time spent on that and also increase the accuracy of digitization. So the second one, which is what I'm currently working on, is called battery automatic defect recognition. So actually, we have a lot of projects, not just on battery, but really developing the advanced analytics for a lot of applications with the CT machines. One being battery, the others include the aviation parts, automotive parts, and also apply it to the visual inspection equipment board scope, really to have the on-edge, on-premise advanced analytics capability to do automatic defect recognition instead of having some human to look at it. And really the idea is like, let's implement the deep learning algorithms really to look at the images and sync it up with the production speed and having it recognize different defect modes and then speed up the output for the human to look at. So we are currently in the progress of developing it, but it has already shown very promising results and going to be in the next product release next year. So this is called what we call Phantom View, which is really an extended reality platform. So we have previously worked on some techniques related to building a universal extended reality platform to facilitate high fidelity visualization. So for example, you can utilize the onboard CV for really static high resolution CAD overlay. And we offload the rendering from the device to a local server so we can do real-time data streams with very low lag. And this also has been applied to some collaborative and cross-platform, which facilitates surgical procedure enhancement. It also has some dynamic 3D model registrations with 3D post estimations, and using the same technology as low latency streaming AR and MR technologies. And this is an example where we use a HoloLens really to overlay some CAD models actually drawn by the doctors and on a skull of a kid who is going to perform a surgery later on. So this is the applications actually developed by Avatars, who is under the ventures team. So this application is called intelligent field inspections. So what they do is they are using panoramic images, imaging capture system to usually with the initial focus on the offshore platform. And the purpose they are going to do this is they want to use either UAV or ground-based to detect corrosion, and exactly the extent and severity of the corrosion. And what they do is they use semantic segmentation really to categorize the corrosion into low, medium, and high categories, as indicated by the green, yellow, and red colors from the imagery, and then help them to monitor the corrosion and probably make some actionable insights for the operators. They also have another application which I haven't included here. It's called like site survey. So they have the UAVs to flying out to a remote site, take a lot of pictures, which can be used to recreate a 3D site map. And they can actually use a lot of images they take to monitor the site. For example, one thing they can do is they can take a picture of the tank at the site and use the shade areas within the tank to calculate how much liquid remained in the tank. And that says another applications of computer vision technologies were used to facilitate a lot of operations in the field. Any questions so far? I think this is the last page of my slide. So really to summarize, we have seen very rapid progressions in deep learning algorithms and improvements in hardware that facilitates advancement of the computer vision technologies. And AI actually has found a lot of success in many of these areas, including machine inspection, automotive, retail, and healthcare. And this trend shows no signs of slowing down. And it's predicted that by 2022, the computer vision and hardware market is expected to reach 48.6 billion. And we have actually become empowered like never before, but we also discover how far we must go before we can understand and replicate one of the fundamental functions of human brain. And I would say in the short term, it's still more likely that AI would be used to augment and extend human capabilities. But long-term wise, we're still optimistic about what AI can do, and we're steadily stepping towards the goal. So again, every one of us can make an impact, and actually we need to work together towards the ultimate object, no matter how small the projects are. With that, I think I will conclude my presentations and leave 6 more minutes for questions.
This is Dan McCormick. I just have a question, not so much on the learning side, but you talked about some of the edge devices that you're using to collect data. Is that the devices, the actual type of devices you're using? Because we have some interest in edge devices. I'm just curious, not that you have to tell me at this moment, but maybe you could send an email with specifics about what kind of devices you're using. You mentioned some that were low power, and I'm just curious about the various types you're using.
Yeah, so they are the sensor side and the processor side, right? So for the sensor, for the quick prototype, we actually use a lot off-the-shelf sensors we actually bought from Amazon. But the edge device is really the core here, because like the one I mentioned, NVIDIA made them. So they have a series of different products to meet different purposes. And they are very powerful in doing edge analytics. And there are also some other providers. For example, we know Intel also offers similar products. We know like Visual team, they're actually looking at using Intel. So yes, I'm happy to connect offline if you're interested to learn more about the edge devices we're using.
Okay, thank you.
And also, if you're interested, I can probably clean and zip, make the slide deck smaller so I can share with everyone. And if we're having any questions that you want to discuss offline, I'm more than happy to do that. I know like we are limited to time today.
Xiaoqing, I'll ask you a question. I I don't even really know how to word the question that I'm thinking of, so forgive me for trying to work through it. But the slide where you had the example where um, the uh, the the thing was trying to determine what number was being drawn between, like, 1 through 9, or 0 through 9, or whatever. I thought, yes, I thought that was like a really, really interesting sort of like description or explanation of kind of how it works. And that was kind of the moment when because like in one of the first slides where you had the video and it was like identifying people and traffic, like traffic lights and cars. I'm like, man, how is it possibly doing that? And it kind of clicked when you showed this slide. I'm like, oh, that kind of makes sense. It has, like a map or several options, and then it's basically calculating the probabilities of, what is it most likely to be. My question is though, what if you don't have that? What if you don't have that map? What if you don't have digits 0 through 9? That seems like that would almost be the harder part. Like, what if you're trying to, like, how could you tell the difference between a pencil and a T-Rex? Like, if you do you always have to have do these kinds of systems always have to have like a context? Like, do they have to know they're looking at traffic specific items, or do they have to know they're looking at letters?
That's actually a very great question, because like, So no matter what the input images, all the images you want to identify, the structure of the deep learning model actually remains the same. So you can either feed training data, for example, like digits, or feed training data like human faces. So once we prepare the training data set, of course, you have to prepare the pictures of pencil versus T-Rex, and also need to categorize or label them so the model has a ground truth to calculate or compare against. That's what they call the error, right? But once we have prepared and feed that into the model, there's nothing we need to change. So the model will actually have the fixed structure and actually learns to figure out the weights or the parameters of each layer by itself. So for example, in the face case, the lower level features will be some edges, and then have some intermediate levels being your nose, eyes, and most advantage one being the faces. So that is figured out automatically, and we don't need to worry about. And the work we have to do is prepare the training data with the ground truth.
Gotcha. Okay, that makes sense.
Mm-hmm.
Thank you. Anyone else? Looks like we got 1 minute left here. No? Okay, well, I guess we will we'll call it here. Thank you so much, Xiaoqing. This was very, very interesting.